For this question, we want to find the domain of the function f of x equals negative 5x plus 7. As we look at this function, we're looking for signs of restrictions on the domain. And what I mean by that is we're looking for a variable to be in the denominator because division by 0 is undefined and the denominator cannot equal 0 because of that. That would be a restriction. You could also look for variables underneath a radical because the square root of a negative gives you imaginary numbers, and that's not in the domain. So when we're looking at the function, we're looking for restrictions like that. This function f of x equals negative 5x plus 7 doesn't have any of those restrictions. More specifically, this function is called a polynomial function, and we have a definition of polynomial functions. A polynomial function is of the form f of x equals a sub n, x to the n, plus a sub n minus 1, x to the n minus 1, plus dot dot dot, meaning that pattern continues, plus a sub 1x plus a sub naught. This is where n is this highest power on x. N is a non-negative integer. I've got a list here of integers, 0, 1, 2, and so on. These are only the non-negative integers. And the coefficients are from the real numbers. So we can see that we have that here. In this example, n would be 1, that highest power, on x, and the coefficients of negative 5 and 7 are from the real numbers. This is a polynomial function, more specifically because of this n being to the first power. We say it's a linear function. Once we recognize that we have a linear function, we can find the domain by understanding that there are no restrictions on functions like this. So the domain of every polynomial function is all real numbers, and we write that in interval notation as negative infinity to infinity. So the domain of this function is negative infinity to infinity, or all real numbers, because the function is a polynomial function, and a polynomial function doesn't have any restrictions. On this question, we want to find the domain of the function g of x equals 9x over x squared minus 4. And as we look at this function, we're trying to find the domain. We're looking for possible restrictions on the variable x. Now, one that stands out pretty quickly to me is that I see a variable in the denominator. And when you have a variable in the denominator, you have to consider division by 0 being undefined. And so you want to look for when that denominator is equal to 0. Now, before we do that, I just wanted to categorize this function as a rational function. A rational function is of the form f of x equals p of x over q of x. So we've got a fraction form when we have rational functions, and then specifically your numerator p of x and your denominator q of x need to be polynomial functions. And those polynomial functions are nice functions where the power on the variable is a whole number. So also right here it mentions that q of x is not equal to 0, and the reason for that is what we discussed just a moment ago, that division by 0 is undefined. So we can't allow that denominator to equal 0. Now over here, this is a discussion of how we're going to find the domain. Since rational functions are in the form of a fraction, we have a restriction that the denominator cannot be 0. You can find the restricted values by creating an equation. The equation is the denominator equal to 0. So that's going to be that q of x, whatever's in the denominator, equal to 0. Remember, division by 0 is undefined. The denominator equal to 0 will give us those restricted values. Once we solve this equation, the solutions to this equation are those restricted values, and they must be excluded from the domain. So let's create that equation for this example. Our denominator, q of x, would be x squared minus 4. We're going to set that equal to 0 so that we can find those restricted values. Now to solve this equation, this is a quadratic equation. There are many approaches you could take. We'll take the approach of isolating the square. So we're going to add 4 to both sides. X squared equals 4. Once we isolate the square, we'll square root both sides to get rid of that square. Square root and square are opposite operations. They cancel each other out, leaving us with x on the left. And then on the right, we're going to gain a plus or minus symbol. Every time you square root a square, you gain that plus or minus symbol. And square root of 4 is 2. So we came up with two solutions to this equation, plus and minus 2. That means we have two restricted values, positive and negative 2. And there are a couple different ways that we can write the domain once we know the restricted values. We can write the domain in set builder notation. In set builder notation, we use curly braces to indicate we're dealing with a set. We're going to use the variable x because we're dealing with the domain. We draw this vertical bar, that means such that. And then we're going to put the conditions on the set. So x is a real number, and x is not equal to plus and minus 2. So any real number not equal to positive and negative 2. And that's because positive and negative 2 make the denominator 0, which makes the whole function undefined. Another way we could write the domain would be in interval notation. So in interval notation, I like to draw a number line. And you're going to mark on that number line the restricted values of negative 2 and 2. We'll mark those restricted values with an open circle to indicate that those values are not in the set. And we can shade all of the other values. So this is a representation of all real numbers except for negative 2 and positive 2. And in interval notation, we want to represent each of these intervals. And remember that negative 2 and positive 2 are not included in the set, so we have to break at those values. We have to break up the interval at those values. So to represent this first one, we need to write the lower bound of negative infinity and the upper bound of negative 2. And we're going to use parentheses on both of those. So that's indicating all the numbers from negative infinity to 2. The next interval has a lower bound of negative 2 and an upper bound of 2. Once again using parentheses, so the parentheses indicate that the number is not included in the set. Just like open circle indicates that the number is not included, parentheses indicate that the number is not included. So this interval is including all the numbers between negative 2 and 2, but not the endpoints of negative 2 and 2. And then our final interval would start with a lower bound of 2 and continue on to infinity. We would put union symbols between these intervals, and this gives me the domain in interval notation. The domain of g of x equals 9x over x squared minus 4. On this question, we want to find the domain of the function f of x equals square root of 2x minus 18. When you're looking for the domain, you're looking for possible restrictions. And in this example, I see a square root. And with square roots, we know that square root of a positive number is a real number. We know that the square root of 0 is 0, which is a real number. However, the square root of a negative is going to give you I, and that is a complex number or imaginary number. So this gives us a restriction on square roots, and that restriction is that we only want to have positive values or 0 values, or we can say non-negative. So I've got some information up here being more specific about radical and root functions. This is obviously a radical or root function because we have the square root. And with radical and root functions, you want to pay attention to whether you have an even index or an odd index. So the index is going to be on the radical right here. In this example, we don't have an index listed, and when an index is not there, we assume it to be a square root. And so we're dealing with an even index. So here's a definition of a root function. A root function is of the form f of x equals the nth root of g of x. And this is when n is an even positive integer greater than or equal to 2. So that's when we have an even index. And when that index is odd, then we have an odd index radical. So what's interesting about the difference between even index and odd index is that it doesn't have the same restrictions. If we have the nth root of a negative and n is odd, that is a real number. So it's only when you have the even index of a negative that produces a complex or imaginary number. So in this example, this is what we're going to follow to find the domain. So taking the even root of a negative number results in a complex or imaginary number. Since we're interested in real function values, we would like the expression inside the radical to be non-negative, 0 or positive. We're going to create an inequality to solve, and that inequality is the expression underneath the radical greater than or equal to 0. So we've made g of x the expression that's underneath the radical, and we want that to be greater than or equal to 0. That's positive or 0 or non-negative. So we erase these markings and we'll work out the domain for this example. We're going to take the expression that's underneath the radical, 2x minus 18, and we want that to be greater than or equal to 0. And that's because we're excluding negative values. We're only including positive and 0. And we solve this inequality. So we're going to add 18 to both sides. That's 2x is greater than or equal to 18. Divide by 2 on both sides to get x is greater than or equal to 9. and this will give you the values for the domain. So you can write that domain in set builder notation. We say x such that x is greater than or equal to 9. Or you can write it in interval notation. In interval notation, you would mark 9 on the number line. 9 is included in the domain, so we're going to put a closed circle on 9. And then we also want our function to be, our values, our x values to be greater than 9. And so I would shade to the right of 9, indicating greater than 9. Now to write that in interval notation, we want to write a lower bound of 9 and an upper bound of infinity. And we'll include a bracket on the 9 to indicate that 9 is included in the set. And we always use parentheses on infinity. So this is our domain in interval notation from 9 to infinity. On this question, we want to find the difference quotient of f, that is, find f of x plus h minus f of x over h, so this is the difference quotient, where h is not equal to 0, for the following function, f of x equals negative 5x plus 6. So we want to do the difference quotient calculation, so we need to do this calculation here. And let's do that calculation by first starting off with this portion of the expression, f of x plus h. f of x plus h is calculated by replacing x with the value inside of the expression. So that will give us negative 5 times x plus h plus 6. And I'll simplify by using the distributive property. I'm going to distribute negative 5 to both these terms. That gives negative 5x minus 5h plus 6. So now that I've calculated that first portion right here, f of x plus h, I'd like to calculate the whole numerator. So I'm calculating the whole numerator, which is f of x plus h minus f of x. And I'm going to use the work that I've already done. So I've already calculated f of x plus h to be negative 5x minus 5h plus 6. And I'm going to put that in this position right here. So that's going to be negative 5x minus 5h plus 6. Then I'm going to carry down this minus sign, and I want to subtract f of x. F of x is the function that was originally given. I want to subtract that function, and because I want to subtract the whole function, I'm going to put parentheses around it. That's negative 5x plus 6. And once again, I'm going to use the distributive property to simplify. I'm going to distribute this negative to both terms. I would have negative 5x minus 5h plus 6. A negative times a negative is a positive 5x. And negative times a positive is a minus 6. I have a little simplifying I can do here. I have some like terms. I have a negative 5x and a positive 5x. And when you combine those together, you get 0. And I have a plus 6 and a minus 6. Those are like terms, and when I combine them, I get 0. So I just need to carry down this minus 5h that hasn't canceled out. So now we've calculated the whole numerator. So now that we've calculated the whole numerator, we're going to calculate the whole expression. That whole expression for the difference quotient is f of x plus h minus f of x over h. And once again, we're going to reuse the work that we've already done. We've calculated the whole numerator here, and that's negative 5h. And we're going to divide by h. The h's cancel each other out, and so this fraction reduced down to negative 5. So the difference quotient for the function f of x equals negative 5x plus 6 is negative 5. On this question, we want to find the difference quotient of f of x equals x squared plus 1. That is, find this difference quotient here. This is the formula for difference quotient, f of x plus h minus f of x over h, where h is not equal to 0, and simplify. So we want to calculate this difference quotient for our function f of x equals x squared plus 1. We're going to take it in stages, so we're going to start by calculating this part here, f of x plus h. So the expression f of x plus h can be found by replacing the variable x with what we have inside the parentheses. So that's going to give us x plus h squared plus 1. And we want to simplify this. So squaring means to multiply the base twice. So we'll multiply x plus h times x plus h. Carry down that plus 1. We'll multiply this out. X times x is x squared. X times h is xh. H times x is also xh. H times h is h squared, and once again carry down that plus 1. We do have some like terms that we can combine together. We have two terms with xh. So when we combine those like terms, we get 2xh plus h squared plus 1. So we've calculated f of x plus h, and now we'll calculate the whole numerator. So the whole numerator is f of x plus h minus f of x. And I'm going to use the work that I've already done. So we've already calculated f of x plus h to be this right here. And so I'm going to carry that down and replace f of x plus h with that expression. So we have x squared plus 2xh plus h squared plus 1. So then I want to carry this minus sign down. And I want to subtract f of x. And f of x is that function that we were given to start with. F of x is x squared plus 1. I want to subtract that function, x squared plus 1, but I want to make sure I subtract the whole function, so I'm going to put parentheses around it. And now we want to simplify. So I'm going to distribute that negative to both terms in the parenthesis, and that gives me x squared plus 2xh plus h squared plus 1. And now using that distributive property, I have minus x squared minus 1. So we have a little simplifying that we can do here. I have some like terms. I have a positive x squared and a negative x squared. Those are like terms, and when you combine them, it becomes 0. We also have a plus 1 and a minus 1. Those are like terms, and when you combine them, it becomes 0. So I'm going to carry down these other terms that are remaining, 2xh plus h squared. So we've calculated the entire numerator, And in my final step, we're going to calculate the entire difference quotient. That's f of x plus h minus f of x over h. And once again, I'm going to reuse my work. We calculated the whole numerator to be 2xh plus h squared, 2xh plus h squared. We're going to divide that by h, and we have two terms in the numerator, which means that we can distribute the division to those two terms. That would give 2xh over h plus h squared over h. The h's cancel from the first term, leaving you with 2x. And on the second term, h squared over h would be h. So the difference quotient for f of x equals x squared plus 1 is 2x plus h.